Okay, and our last speaker for this session is Julian Erhard from the Technical University of Munich, who's going to talk about when to stop going down the rabbit hole, timing context sensitivity on the fly.
Thank you very much. So this is joint work with Johanna Schinabeck, Michael Schwarz, and Helmut Seidl. And I would like to start with a motivating example. So here you can see a very simple recursive program with some main function that calls some recursive function f that calls itself with a decremented parameter. And this will go for a while and call itself 100 times. And now let's assume that we want to analyze this program with a context-sensitive static analysis that uses, for example, an interval abstraction. So how would we go on to do that? So at first we would start from the function main, and we would have to look at the function call that is happening there. And for that, to analyze this function call, we would analyze the function f in the context where x, the parameter, is 100. And now, of course, we would again have to analyze the function call that is happening within this function invocation. And we would have to look at the function f in the context where x has the value 99. And again, we would have to look at another function call, this time in the context where x has the value 98. And this would go on for quite a while until we enter the rabbit hole, so to say, and hopefully come back. So in this case, there will be an end, and when x reaches the value 0, we will be able to come back. But there will be recursive programs for which this will not terminate, and we will continue to look on further and further contexts. And that may even be the case when your recursive program always terminates, because you have some over-approximation that leads you to look at more and more contexts. And so if you come back from this rabbit hole, then maybe then you can compute the states after the course of all these functions. Okay, so that's certainly something that in some circumstances we want to avoid, and we want to have some trade-off between analyzing everything context sensitively and ensuring that we terminate. So what is our goal? Our goal is to limit the context sensitivity dynamically so that we are able to deal with recursion by still in general being context sensitive. And we don't want to touch all our existing analysis implementations, but instead reuse them as is. And additionally, we would like to avoid having to do some pre-analysis. So because a pre-analysis may often be imprecise or be costly. So what I just want to highlight some related work. There has been lots of work on how to tune context-sensitive analysis, but I just want to highlight something that is called selective context sensitivity, which follows the principle that you perform some pre-analysis, and then judging from this pre-analysis, you decide the level of context sensitivity that you apply in different places and for different functions. And for example, you may perform some pre-analysis that computes a call graph, and based on that, you decide that you analyze all functions that appear in any cycles that happen in the call graph context insensitively. But these approaches, they rely on pre-analysis, and here we want to present some approaches that do not rely on any such pre-analysis. So we propose 3 such approaches that allow us to tame context sensitivity, and they are called context widening, loop recall string, and context guess. And to avoid to change existing analysis implementations, we implement them as decorators or as wrappers around existing analyses. So to be able to understand how such a wrapper would work, let's have a quick look at how an analysis is defined. And so clearly for an abstract interpretation-based analysis, we need some abstract domain. We need, for context-sensitive analysis, we need some set of contexts. That is the set of contexts according to which we distinguish function calls, and some abstract semantics for program actions. And as we are interested in function calls, we demand that the way that the callee start state is computed, as well as the context, is clearly defined in the existing analysis. So we will call this function enter that does this. And to go with that, there will be some function combine that from the end state of the called function and the preceding state of the caller will compute the new caller state. And now let's quickly visualize that. So assume we have in the context C some function call at this edge here. We will first, using the function enter, compute the start state of the called function, and we will compute some context CF compute some context CF. Then, as usual, we will analyze the function and come up with some state at the end of this function. Then, using the function combine, we can take the state at the end of this function f in this particular context, together with the preceding state of the caller, and compute the new state, caller state. And so what our analysis lifters or analysis decorators have to do in particular is that they will have to define this enter function appropriately, potentially using the enter function of the underlying analysis. And now I want to quickly talk about context widening. So this is the first approach that we propose. And the idea here is that we use the widening operator that is already given by the domain to limit the number of contexts that are encountered when we analyze recursive procedures. And you will find more on that in the paper. And the next approach is called the loop-free call string, where we abstract call strings by representing cycles that occur in a call string by sets of the involved procedures. So, yeah, so this is some abstraction of the call string approach that gets rid of these cycles. And now I want to talk about the context guess. And the idea here is that we add some counter value, some guess, as part of the abstract state of the domain. And whenever we encounter a function call, we decrement this gas value and pass this decremented value to the callee. And in case the gas value has ran out, we use some fixed element out of this context, some bullet context as the context. So this ensures that whenever the gas has run out, that we use the same context, and all calls with zero context gas are analyzed in the same context. And so now let's have a look at the example again. We assume that we analyze the same program from before, now with some initial context gas of 3. And now we will have a look at the first function call. And there we will pass now the context gas, which is decremented compared to the caller state. So we pass a context gas of 2. And for the next call, we pass a context gas of 1. And now, for this call that happens here, we are in the situation that our context gas has ran out. And at this place, we actually now decide, okay, we do not use a context that contains all the information that we have usually, but instead we just use some bullet context. And now that ensures that when we here perform or analyze the next function call within this function f in the context bullet, that we actually will reuse the same context again, because the gas again has already run out. And here, so the first we will, in this case, have reached this node again with the value of 97 for x. And then our fixed point algorithm will then actually perform widening so that we can then compute a solution for this function invocation. And then based on that, we can compute abstractions for the states of the other, after the other function invocations that we have seen. Now, how does this turn out? And so we have made some experiments on SVCOM tasks, and I want to in particular highlight some experiments on recursive, on a set of recursive SVCOM tasks that you can see here. So here you can see the full contexts as were shown in the initial example, and the call strings of unbounded length. And you can here see our 5 configurations with the loop-free call string, the context widening, and 3 configurations of context gas with different initial gas values. And so all these approaches were implemented in Goblint. And alongside with a completely context-insensitive analysis, as well as a 2 call string and a 10 call string analysis that we have here for comparison. And what you can see here is the number of correct verdicts on these tasks. So these were about the no overflow property, so whether we could show for a task that it contained no integer overflow. So these were all very integer heavy programs. So that was the task. And so with the green bars, you can see the number of correct verdicts that each configuration produced. And in red, you see the number of stack overflows or timeouts that were produced. So you can clearly see that for the full context and unbounded call string, you get lots of stack overflows or timeouts. So almost half of the task resulted in such a resource exhaustion. And now for our approaches, for the loop-free call string and the context widening, you can see that we do not have any such stack overflows or timeouts. And then unfortunately, the precision decreases compared to the full context approach. Now for the context gas, you can see that actually we get quite good results regarding the precision. And this is, for the higher context gas, you get actually better values with regards to solved tasks compared to the full context analysis. Unfortunately, for higher context gas values, you also get some stack overflows or timeouts. Okay. And so in this case, on this set of benchmarks, this context gas of 30 yielded the best results and better results than the full context analysis. Now, to conclude, we have proposed 3 means to tame context sensitivity, context widening, loop-free call string, and context gas, and they are implemented as decorators for existing analysis so that you do not have to adapt your existing analysis code. And these approaches manage to reduce the number of timeouts and stack overflows of recursive tasks. And albeit the precision for the loop-free call string and the context widening was decreased, we see promising results in particular for the context gas with regard to the precision performance trade-off and more solved tasks than a full context analysis. So that's it. So thank you.
Thanks a lot. Very interesting work. I was wondering, particularly for the loop-free call string representation, why does that lose any precision? Isn't that an equivalent representation of what you would normally have?
Compared to what do you mean?
I mean, normally, I guess you would have, just a repetitive occurrence of that function in a rather lengthy call string, right?
Well, no, there may be. So there may be. So it's not ensured that the cycle is always of the same form.
I see what it. Okay, there's work. I'm not sure if you're aware of it on push-down systems that actually model these context strings. Also, well, they basically have loops in their representation, but that's more precise than what you have. So if you haven't looked into this yet, I would recommend that you have a look.
Okay, yeah. So we have there's lots of work, as I said, on different on all of these context sensitivity, and yeah, there are some other approaches on how to handle these call strings also. Yes.
All right. Thanks.
Thank you.
So we've looked into something similar, not for call strings, but for access path in taint analysis, where you have the problem with doubly linked lists, for example, that you're always going pref, next, and you're always returning to the same object. And if you put them together in a simple way where you just say, oh, I seem to be repeating myself, then you could actually generate false positives on that one, because you don't see when someone is kind of FG next versus just F next, because then you might also kind of stop in the middle. There are some of these corner cases. Have you experienced cases in which you lost precision due to that?
With regard to what approach?
With these loop-free call strings, where you're cutting things out that look like a loop, but they are not actually loops, which is not the problem of the concept, but of the detection when you should consider things a loop and when not.
So I mean, we have not looked too much into detail for the single tasks that were not solved anymore. So I cannot really report on that. But yeah, I mean, clearly the issue is that you just the amount of context that is distinguished is too small with regard to that approach to really obtain good precision.
Thank you.
Hi, cool talk. Can you go back to the results slide?
Yeah.
So the context gas goes up to 30, but the call strings stop at 10. So I was curious what happens if you set the call strings to 30.
Okay, so we have not actually tried that here, but we have made, so this is just a subset of the experiments, and we also tried some larger benchmarks, and we see that the 10 call string already tends to perform worse on larger benchmarks, so it has larger runtimes. And so the
Worse than the 30 gas.
yes, so
Okay.
the thing is that due to the call strings, you distinguish more. You distinguish on the call strings, and so our analysis are not really, or mostly not interested in the call string, but on the abstract state. And so you introduce some artificial distinction between abstract states or between contexts that is not really useful for the analysis.
A quick follow-up on that. If I reach a function with the same abstract state from two different paths, except
Yes.
the gas is different, do I
Yes.
analyze it twice or once?
So that depends. So usually you would reach it with a lower value the second time, or a value that is as high, and in that case you would not reanalyze it again, because the way we have defined the ordering on the abstract state is such that on a join the higher gas value is maintained. And so if you come back the second time, the higher value that was reached, that has reached the first, is maintained. So you do not have to reanalyze it. So that's a nice twist. But of course, in the rare circumstance that the second time that your fixed point solver comes there and you have a higher gas and the second time, then it may increase actually, yes, and you would have to compute.
Okay, last question.
So I'm wondering, what is the difference between the context gas and conceptually just unrolling the recursive call? Is there any difference?
So the point is that we don't give up on when the context gas has run out, but we just, well, it depends on, well, so you do still a context insensitive analysis, and actually you join all the calls together from everywhere that reach this function with context gas 0.
So one question also about this context gas idea. So does this mean with this technique that the result of the analysis suddenly depends on the order that the analyzer chooses to visit the different parts of the program? So it may run out of gas differently depending on basically the work list order or something like that. So you end up having like a non-deterministic result of the analysis.
I think that should not be the case. So we actually, I have not given it, I have not considered that in very much detail yet, but I think, so the gas value should always be computable by the shortest path with which you can reach this abstract state. Or with which you reach the function invocation.
There's time here. Okay, so let's say you have like an if-else branch, and then you have calls in both the then branch and the else branch, and then decide, depending on which order you visit the then and the else branch, then maybe you run out of gas while looking in the then branch before you get to the else branch, all the way around.
So within a function, you maintain the same context gas value. So it's only for the called function that you decrease the context gas value. So it will.
Yeah, maybe let's take it offline. So yeah, time for the break. Okay, well, let's thank thanks the speaker. Let's thank the speaker again. So we'll come back to our last session at 4 p.m.